So welcome everyone to the Journal Club of the Physical Review Journals. My name is Kjaergaard. I am an editor of the Physical Review. Before we start with the event today, let me just tell you a few words about what is this event, right? So the Journal Club is a new initiative from the Physical Review Journals, and our idea here is really to promote the latest results, to highlight the latest research results published in our journal. So to bring to you outstanding authors for a nice conversation. So at the same time, we also want to promote early career research. So we hope this becomes a platform for them to share their ideas and connect to this community. In the paper today, this was published in our recent journal. We just launched it, PRX Quantum. So I just want to tell you also a few words, a few words about this journal. So our aim here is to create a home for this specific community here today, for the ones working with quantum information science and technologies. So this is a high selective and open access journal. And we have already a few papers online. So I encourage you to take a look in our website. And also in there, you're gonna find an editorial where we explain our vision for this journal. And I hope you also benefit from the fact that the APC are waived until the end of the next year. Coming back, I'm sorry, I'm having some trouble to do the slides. Okay, so I also wanted to tell you a few words about Zoom. So during this meeting, so please try to keep muted, so you can see here in the lower panel of Zoom where you can mute and unmute yourself. If you click in the participants, you're gonna see some right-hand panel that appears, that you can raise your hand for ask questions, but also at any moment you can use the chat button down in the Zoom panel, where you can type your questions, and then our moderator is gonna call you, and we hope you can speak your question out and loud to everyone and use your camera as well. So the idea is pretty much to have an interactive meeting. We'd like to have nice conversation. So finally, coming back to our meeting. So today, to help guide this conversation, we have here with us Dr. Gerhard Kirchmair. So Gerhard is a professor at the Institute of Experimental Physics in the University of Innsbruck. And he's also a junior research director at the Institute of Quantum Optics and Quantum Information, also in Innsbruck. And his research interest covers a broader range of topics. But to mention a few, he has published several papers in superconducting circuits, which we are going to hear a lot today. But he is also interested in optomechanics, quantum simulations, and quantum sensing. So Gerhard, welcome to the screen. I leave now with you. You're muted, Gerhard.
Now it should work, I guess. Yeah, thank you, Katyusha. Thank you, Stoyan, for having me as a moderator, and for this nice series, which sort of gives the community a nice opportunity to interact with each other. So before I introduce the two speakers of this colloquium, let me just briefly go over some, timings and so on. So it's again 20 minutes. So we will have two presentations, sort of about 10 minutes each, sort of roughly split in half. And as Katyusha already said, if you want to ask questions, put them in the chat or raise your hand. I think the idea is, unless they are really sort of brief questions, we should have them at the end, because you have plenty of time to discuss the questions afterwards. So all in all, we have about an hour or so. And yeah, so I'll at the end try and coordinate a bit, sort of maybe not necessarily take questions in the order they come, but if I see questions which sort of, you know, could be combined, I'll try and make sort of a package out of this and sort of then ask the person putting the questions down to maybe ask them in person. It would be nice if you could switch on your camera to do that we actually see you. Yeah, so let me now introduce the two speakers of this journal club. It's sort of split in two halves, as we have an experimental and a theory part. So Félix Beaudoin will start with the theory, and he completed his master's degree on the theory of superconducting qubits at the University of Sherbrooke with Professor Alexandre Blay. He then did a PhD on the theory of spin qubits at McGill University with Professor William Keusch. And then until 2019, he worked as a postdoctoral researcher and lecturer at Dartmouth College, where he carried out research on quantum control, quantum metrology, and quantum noise spectroscopy in the group of Professor Lorenza Viola, who's also here today. This is all done in collaboration with the group of Professor William Oliver at MIT. So this is also the paper we'll be hearing about, was performed experiments at MIT. And yeah, Dr. Beaudoin joined Nano-Academic Technologies in January 2019 as a research scientist and software developer, where he actually leads the development of computer-aided design tools for quantum technology. Then the second half of this journal club will be sort of focused on the experimental part of the paper, and it will be presented by Uwe van Lüpke, who did his bachelor and master's in the Karlsruhe Institute of Technology, where he worked in the group of Dr. Johan Popp on high kinetic inductance materials for circuit QED applications. In 2018, he finished his master's with a thesis in the group of Professor William Oliver on 2-qubit spectroscopy experiments, so essentially the work he will present today. And then in 2019, he moved back to Europe and joined Professor Yiwen Chu to build up a laboratory at ETH Zurich to research hybrid quantum systems made of phononic resonators and superconducting qubits. So yeah, those are two speakers for this journal club, and they will tell us more about, I think, a very relevant topic, especially for multi-qubit devices, where we are concerned with noise and how sort of correlations in the noise affect the performance of such a large computer. And essentially, they will tell us more about how they developed and actually implemented techniques that, you know, tackle this problem and allow us to characterize these larger systems. So please, Felix, I think you will start. Go ahead. I think you're still muted.
Okay, do you hear me?
Yes, now we can hear you.
I'll try sharing my screen again. I apologize for the slight technical delay. Do you see my screen? And do you see my slide as full screen?
Yeah, it's good.
Thank you very much. Let me start right off the bat. Thanks a lot for the introduction. And I'd like to actually thank the organizers, Dr. Casimiro, Dr. Reddick, Dr. Kirchmair, for the amazing job they have done organizing this journal club. I feel very lucky to be here. As already mentioned, this talk will be divided in two parts. I will be presenting the theory, and then my colleague Uwe from MIT will present the experiment that follows. To motivate this work, we can say briefly that quantum technology has seen some tremendous progress in the last few decades, in particular in the subfields of quantum computing, quantum sensing and metrology, and quantum communication. And all of this progress is based on quantum hardware, which, however, is notoriously sensitive to environmental perturbations and noise. And ultimately, the properties of this noise is going to dictate the extent by which classical limitations will be overcome in all of these technologies. In particular, in terms of noise properties, we're thinking of spatial correlations, which refer to the interrelationship or degree of correlation between the noise affecting spatially distant qubits. Excuse me. By temporal correlations, we refer to memory effects, or in the Fourier picture is the noise spectrum flat or colored. And here by quantum noise, we refer to the nature of the interaction between the bath and the system. In particular, is this interaction due to a classical stochastic process or to a non-commuting quantum operator? So all of these properties have different impacts on the performance of quantum technologies. In particular, long-range spatial correlations have been shown to imply more stringent threshold requirements for quantum error correction. And because of this kind of profound impact of noise properties on quantum advantage, it is highly desirable to fully characterize the noisy environments that afflict our quantum systems. This will be useful for validation of microscopic models of noise, but also for the design of control strategies that are optimally tailored to specific environments. There is, of course, a very extensive and very wide body of literature available of noise characterization methods that is more extensively covered in the introduction of our paper. But here, let me mention that single qubit noise spectroscopy techniques have been applied experimentally across a very, very wide range of qubit platforms. From the theory side, there have been very promising proposals for the spectroscopy of noise in multi-qubit systems already. And there have also been experimentally some measurements of specific spatial correlation measures in spin qubit and superconducting qubit systems. But what is lacking, in our opinion, in these experiments is a measurement of the full-fledged 2-qubit spectra defined as follows here. So here we are interested in a system consisting of 2 qubits that are coupled to a shared noise source. And these 2 qubit spectra are defined as Sjk of omega, where J and K are indices referring to either qubit 1 or qubit 2. And these spectra are defined as the Fourier transform of the correlation functions of the Bath operators Bj and Bk for qubit J and K. And so we see instantaneously that these spectra, they can be divided into two categories. First, the self-spectra, which are real quantities that characterize the temporal correlations of noise affecting each qubit individually. And there is also a cross-spectrum, which is a complex quantity, which simultaneously characterizes the temporal and spatial correlations of the noise between qubit 1 and 2. And in addition to these spatial temporal correlations, these spectra also capture the quantum character of noise in the sense that if these Bj and Bk are non-commuting quantum operators, then it follows that the spectra may be frequency asymmetric. So to characterize these properties, here we design and validate a protocol for 2-qubit spectroscopy of quantum noise. An advantage of our protocol is that it is continuous wave, and this will enable to avoid complicated trains of pulses that are associated with dynamical decoupling based noise spectroscopy techniques. Another advantage of our approach compared to previous theoretical proposals is that no 2-qubit gate or entangled state will be needed, and this will considerably simplify the experimental implementation. Our protocol is based on the spin locking technique, which was implemented in a single qubit context before that. To describe spin locking, we write a Hamiltonian in 3 parts. The first part is the system Hamiltonian, and it describes 2 qubits with frequency splitting omega qj, and under continuous driving with drive frequencies omega dj and equal Rabi frequencies omega. In addition, we have a system Bath term where we assume that the Bath couples through operators bj and through Pauli operators sigma zj of the qubits. So in a lab frame, without the drives, this would be purely phasing. In addition, we have a Bath Hamiltonian, which we leave unspecified. So we will assume resonant driving. So the drive frequencies are equal to the qubit frequencies. and we will move to a rotating frame at the drive frequencies and perform a rotating wave approximation. And then the next step is we rewrite the Hamiltonian in the eigenbasis of the sigma x operators, which we denote by plus or minus. And in this eigenbasis, we also introduce two new Pauli matrices, tau x and tau z, where tau z is diagonal in the eigenbasis plus minus. And so with these new Pauli matrices, our Hamiltonian takes the following form, and we see that the system part is now given here, and we see that the effect of the drives is now captured by two effective or dressed qubits, which are split by the Rabi splitting omega. And additionally, the system-bat interaction is now transverse to the quantization axis of these dressed qubits. And to turn this to our advantage, we will derive a master equation by tracing out the bat and using the following approximation. So we assume weak coupling between system and bat. We take a secular approximation, and we take a long time limit in which the qubits become sensitive to the noise spectra only over small frequency windows around plus and minus the Rabi frequency. The width of this window is proportional to the inverse of the evolution time. So in this long time limit, we arrive at this master equation here, where the dissipative terms divide in two parts. First, there is correlated decay at a rate proportional to SJK of minus omega. And then there is correlated absorption at a rate proportional to SJK of plus omega. Here, let me pause and note two things. The first thing is we only use fairly generic assumptions that apply across a wide variety of experimental platforms. So this will be applied later to superconducting qubits, but we could also think of applying it to other qubit systems like NV centers, spin qubits, or trapped ions. And in addition, we know that all 2-qubit spectra of interest under weak coupling are present in this master equation, so that the proper choice of measurements may enable us to reconstruct these spectra. And this is what we are going to do using the following control and measurement cycle. We will initialize the 2-qubit system in a state within a set rho S, so we'll successively try each of these states. We will evolve the system under the noise spectra and the drive for a set of evolution times. And finally, we will perform a measurement on the system, and we will consider observables within, again, some set of observables. More concretely, to reconstruct the spectra, we will consider spectroscopy as a nonlinear regression problem. So we will have experimental data here, which we collect in these sample means, O alpha bar, and alpha is an index that simultaneously labels all the chosen observables, initial states, and times. So for the observables here, we consider products of Pauli matrices, and for initial states, we consider product states in the dressed basis. We will compare this experimental data to a model, which is obtained by finding the expected values of the same operators. And we find these expected values by solving the generic master equation for a given spectrum vector, which simply collects all of the 2-qubit spectra of interest at plus and minus the Rabi frequency. And then we will find the spectrum values that globally minimize deviation of model and data. And this will give us these SJK at plus and minus omega. And naturally, by sweeping the Rabi frequencies, we can reconstruct the spectra over a range of frequencies of interest. To formalize this, we define our estimate of the spectrum vector S through an M estimator, which is defined like the value of S that minimizes a loss function lambda. And the loss function lambda, it penalizes deviation of observations from expected values normalized by the standard deviation of the observations. There are many possible choices of loss functions. The most natural one is the quadratic loss function, which is equivalent to ordinary weighted least squares. But additionally, we also consider the Uber loss function, which is equivalent to weighted least squares over an interval from minus delta 0 to delta 0. But outside this interval, the Uber loss is proportional to the absolute value of the deviation instead. Here, delta 0 is called a tuning parameter, and it is chosen arbitrarily. The advantage of the Uber loss function can be seen in the following cartoon. If you perform a measurement experimentally as a function of time, but due to some isolated experimental error, there is some outlier, then weighted least squares will give excessive weight to this outlier, and the fit may deviate substantially from the majority of the data points. This effect is, however, mitigated using Uber loss. And this is particularly useful for large data sets that are characteristic of, that are going to be present in multi-qubit spectroscopy, because in this situation, it is very costly and difficult to manually identify and eliminate outliers. So this concludes what I had to say about the theory part. As mentioned earlier, we expect this this proposal to be applicable across many qubit platforms, but in the next talk, you will see how it was demonstrated experimentally with superconducting qubits.
Thank you, Felix, for this first half of the talk. So maybe, yeah, let's thank Felix. Yeah, clapping is kind of hard here. And then let's hand over to Uwe for the experimental part of the paper. Please.
Thank you, Gerhard. Thank you, Felix, and thanks to the organizers for the opportunity to give this talk. After you heard now how the general protocol works, I will show you how we implemented it in a circuit QED platform. Come on. All right. Okay. So I'll start with how we created a source of correlated noise, since we want to perform a measurement of a noise source that we know the spectrum of, so we can validate our protocol. Then I'll move on to show you how we can use the spin locking relaxometry technique for a measurement of 2-qubit noise, and then finally demonstrate how we reconstructed the 2-qubit quantum noise spectra using this protocol. All right, so what we want to do is engineer a noise source, which is represented by this cloud, and which is coupled to 2 qubits in a kind of symmetric way. And then how we do this is we built this superconducting qubits chip, which has two. Let me remove the zoom picture. Sorry. So which has 2 qubits on the bottom here. These crosses with the Josephson junction on the bottom, at 3.5 and 4.5 gigahertz, so they don't accidentally couple to each other. And then each of the qubits has the individual readout resonator here. And in the middle, we have a common bath resonator, which is coupled to both qubits. And we insert noise into the center resonator. So how this works is we apply a coherent drive with some amplitude epsilon, which is detuned from the center frequency of the common resonator by some frequency delta C. And then this resonator also has some damping rate kappa, and this will cause a steady state photon number of n bar to build up. Then how this looks in the frequency domain is here in blue dashes. You have the spectrum of the resonator, so the transmission function of the resonator with kappa, and detuned from the center of this resonator, we apply a coherent drive with detuned by some value delta C. This will cause a photon shot noise spectrum to build up, which is in amplitude proportional to the number of photons in the steady state. And in the reference frame of the center resonator, it is detuned to a minus delta C. Okay, we can use another effect of these of the coupling between the qubits and the center resonator to calibrate the photon number that we put into the cavity. So we apply this drive, and there's some steady state photon number, and this causes the qubit frequency to shift via the dispersive shift by some value 2 chi n. And we can use this to then have a calibration between the power setting on our instruments and the photon number that we can later use to reconstruct the spectrum. Taking a step back, I want to give you a short intuition on why this spin locking sequence that Felix presented is sensitive to these noise components of dephasing noise. And this was presented in this paper from the MIT group in 2013. So in a single qubit case, if you have your 2-level system, you Rabi drive it on resonance, then it will hybridize to form a dressed state qubit, between the plus x and the minus x state. And naturally, in this inner two-level system, in this stress state qubit, there will be some decay, and this decay is associated with the loss that is perpendicular to the axis of the energy quantization axis of the stress state qubit. And then in the single-gate qubits, you have an analytical solution where you can relate the decay rate under the spin-looking sequence to the spectrum of the sigma z noise at this particular Rabi frequency, or your energy level splitting, which you can easily change from the outside. And then repeating this for different Rabi frequencies, you can probe the spectrum. For 2-qubit case, unfortunately, it's not so easy because there's no analytical solution for the 2-qubit evolution. So we compare it to a numerical master equation simulation. So this is again our sample, and we apply our coherent drive at some detuning delta. And then we apply the spin locking sequence to both qubits, qubit 1 and qubit 2, and each qubit will listen at its respective energy level splitting. So qubit 1 will listen at frequency omega 1, and qubit 2 will listen at frequency omega 2. And we expect correlations to arise between the two stress state level qubits if, and only if, hopefully, both of the qubits listen to the noise that we added to the center resonator. So in other words, if omega 1 equals omega 2 and equals delta. Okay, so the experiment we performed works like this. We keep the Rabi frequency of omega 2 equal to the noise drive detuning. So qubit 2 is already listening to the noise. And then we sweep the Rabi frequency of qubit 1 across this detuning. And then we correlate the single shot readouts of the two qubits while our noise drops on. And the result you can see on the right here. So this is a sketch of the noise spectrum that we put in. And here you can see the correlation between these tau operators that are basically the Pauli matrices for the stress state level qubits. And you can see a few things. So the first one is if qubit 1 has a Rabi frequency that is off resonant with the noise, there is no correlations building up. So in this area and up here. And the next thing is that if it is on resonance, there will be some correlations building up as we expected, and then they will decay to a negative steady state. This was surprising to us at first, but there's an intuitive explanation for it, which is that once the stress state level qubits start to decay, there is each qubit acts as an effective environment for the other qubit, and then one qubit will lose its excitation into the other qubit. Then, because they're basically two-level systems, then you will find them more often in a anti-parallel state than in a parallel state, and you can see this as a negative correlation here. Okay, and the third thing that I want you to note is that this area of correlation building up narrows with time as pretty much 1/t. And the reason for this is that the qubit's response to the Rabi drives gets narrower the longer you apply the Rabi drives, also in a 1/t fashion. So this makes sense. Okay, so this we can use to probe our spectrum, because if we have both qubits tuned to some part of the noise spectrum, we expect them to pick up some correlation which then enters the dynamics, and we can compare this to a master equation with the spectra as fit parameters. So this is basically our way of saying, well, we can now decide which part of the spectrum we want to look at. So we can, in a frequency selective way, measure the correlation between the two qubits. Okay, we also compared this experiment to a simulation of the qubit dynamics using the experimental parameters, and the simulation agrees very well with the experiment. Okay, now how do we use this to reconstruct the spectrum? Well, we take the center line of this experiment, which you can also see on the left here. So there's some correlation building up, and then it decays to some negative steady state. And we repeat the center line because this is where most of the correlations are building up, but we sweep the Rabi frequencies at which the qubits are located. So here we keep the Rabi frequency for both the stress state level qubits the same, and then point by point map out the spectrum. by, as I said, and Felix explained in more detail, fitting the evolution to a master equation simulation with the spectra as parameters. And then this is the first half of the result. So our result will our simulation will give us the spectrum vector, which contains the qubit self spectra and the qubit cross spectra at both negative and positive frequencies. So here you can see that the photon shot noise, which is the black curve, so the theory for the photon shot noise, is reconstructed. So the reconstruction points you see in red. And we capture both the noise at positive frequencies and the noise at negative frequencies. However, our reconstruction, so the red arrow bars, on average lie a little bit above the black line. And this is due to the fact that there's other noise present in the system. The photon shot noise is not the only noise, as we know, since our qubits also decay if we don't put photon shot noise in. Okay. Now the main result. We also reconstructed the cross spectrum of the two qubits. So this is the S12, and this is a complex quantity that also exists both at positive and negative frequencies. And the agreement between the reconstruction and the expected spectrum of our noise source is quite strong. So we reconstructed the real part that is supposedly the only non-zero part of the spectrum. But the reconstruction also captures the imaginary part, which is related to a time delay between the two qubits by this. Yeah? And the so-called non-classical or quantum spectra, which is the asymmetry between the positive and the negative spectrum. All right, with this I want to conclude. So we generalized the spin-locking relaxometry to a general protocol able to perform two-qubit spectroscopy. And this is also, as Felix said, applicable to other systems, so it's not limited to circuit QT, but we applied the protocol in a circuit QT setting and reconstructed the two-qubit spectrum. And then, as maybe an outlook, so one takeaway for circuit QT architectures would be to avoid shared resonators with residual photons in them, because the correlations do build up rather fast. And we used small photon numbers on the order of 0.1. And maybe residual photons from pulses or from thermal photons might also cause these correlations. So in a larger architecture where you don't want these correlations, you should probably avoid this or somehow depopulate your resonators. And then one more thing is that our protocol doesn't need any entangled states to begin with or need any two-qubit gates. So it's rather straightforward to be implemented on other qubit systems. Of course, some of that decreased complexity we outsource to the simulation of the master equation then. Okay, and with this I want to thank all the people that were involved in this project. So here you have a picture of the MIT group and the Lincoln Laboratory group who made the sample. And on the right there's the theory group from Dartmouth. Okay, and now I want to also flash this headline picture. All right, thank you very much.
Yeah, thank you, Uwe, for this very nice second talk. Maybe everybody can switch on his microphones or sort of like push on that clap button. So thanks again to both speakers. Yeah, and before we go into the questions, maybe let me add, so besides Uwe and Felix, we have other co-authors of the paper here. So Lorenzo Viola, William Oliver, and Lee Norris are here. I think that's all of them, who can also answer questions. So please, put your questions in the chat, raise your hand such that we can get started with the question session. Don't see. Okay.
Okay, perhaps I start with a simple one.
I have a couple.
Okay, Uwe,
please.
Can you tell us what was for you some challenging part in this experiment, so that we get a bit of a feeling what is how to...
Yes, of course. So One challenge that we faced initially was that adding these photons to the center resonator, if you add too many photons, your qubits just dephase very fast, and then you have a small signal which, depending on the qubits, might be shorter until the qubits dephased, then shorter than what you need for the correlations to build up. So in the beginning, we used too many photons, for example. And then thanks to the equipment we had available at MIT, we could use also many averages to FP based without.
Okay, thanks. We have one question in the chat now, so maybe so I don't see the people who raised their hands. Sorry, I can't see that somehow.
So if you click in participants, Gerhard, can you?
Okay, maybe.
You see now,
Yeah.
we have two there.
Okay, so then maybe, yeah. So then maybe let's start with Matt Eager from actually PR Applied. Maybe you can switch on your microphone and ask a question yourself.
Yeah, could we go back to one of the last slides from Uwe's presentation?
This one?
So on the bottom right,
Yeah.
the 1.8 to 2.2 megahertz. Yeah, it looks like those, the experimental signal and the prediction are exactly out of phase. Is that just an accident, or is that real, or why?
So thanks for the question. That's a good point. I actually never noticed that. So in general, the smaller parts of the spectrum, so the tails of these and the imaginary parts, the noise signal is very weak, so it's a little bit hard for the algorithm to find the correct values. So I would say it's within like understandable deviations. And then I don't know if there's actually a minus error. I would doubt it, because the code just plots everything for the same way. So thanks for noticing that. I actually don't know why that's the case. Maybe,
yeah,
maybe
it's all pretty flat, but it just looked like it to me. So I thought I'd ask, because I couldn't see why that should be offhand.
It's a good question. Maybe I can tell a few more words. I agree with Uwe that this is probably, if you look at the error bars, this is probably not very significant on the right-hand side. And on the left-hand side of this plot, you can also see that the real part seems to be in phase with the simulation. So I don't know. For me, it's difficult to say if this effect is truly significant.
Okay, thanks. So maybe let's start with one of the first questions in the chat by Malay Singh. So maybe you want to ask it yourself again.
So hi, I'm Malay. I'm joining in from Munich. So in the device schematic, I see a common feed line which you use to both drive and measure qubits, right?
Yeah.
This is slightly non-standard, and I'm trying to evaluate. Let's say if I want to do this experiment for my devices, yeah, how would I go about it? So how would your results generalize to architectures where you have dedicated single qubit drive lines and readout resonators, but also is this kind of a device necessary for your experiment, or could you have done it with a standard device?
Yeah, thanks for that question. So the common feed line is not necessary. I think this was the result of, so when I made the sample, I had a sample that I based it on, and this other sample had a Purcell filter that I just cut off the capacitances on each side to have a common feed line, because I didn't really need the Purcell filter, and it made hitting the right frequencies easier. So if you point out also that the center resonator is seems to be pretty important for this setup. So here we created this photon shock noise source, and for this we needed the center resonator, because it's really quite an easy way to have a well-controlled correlated noise source where we also know the spectrum of. In the end, of course, you would want to notice or a native correlated noise sources. For example, vibrations in your sample could be significant for spin qubits, just out of the blue. And there, I don't think you want to build in like another piece of circuit to generate noise. Right, once you're looking for native correlated noise sources, but this wasn't the case for us, so we built this in on purpose. Of course, people do tend to build individual readout resonators. So if you imagine the sample that we have just without the center resonator, then you could argue that the frequencies of the qubits are so far apart that they don't feel any correlated noise from this feed line. Yeah.
Okay, thank you.
So you don't need it, and you can basically do it also with single qubit drivelets and real.
So maybe we can add a question by Aking Singh, which I think also fits sort of there. So maybe you can ask your question.
Hi, I'm Akhil. I'm joining from Tokyo. Thanks for the nice presentation. And I just want to know that, okay, since you have 2 qubits and they are coupled through the common resonator also. So when you drive both of them at the same Rabi frequency, so you should get some static ZZ coupling, or like, how do you discriminate the correlation which you are measuring with other sort of couplings, because there would be some mediated coupling through the common resonator as well.
Thank you. That's also a very good point. The static ZZ coupling between the physical qubits we can measure in advance, and we determined it, and it's not enough to cause this correlation, especially not the frequency sensitive correlation. And the coupling between the dress state qubits, so the two-level systems that arise when you spin lock drive your physical qubits, that one you can also determine by performing the same experiment that we did. Right, it's not clicking. Okay. Here, but without the noise drive. Just everything is the same, but the on-off setting on the noise drive is off. And then there's no correlation building up. And just some randomness on the other side.
Okay. Thanks. So maybe the next question is by Santiago Hernandez Gomez, who raised his hand. So maybe you can ask your question.
Yes, hi. Can you hear me?
Yes.
Yes.
Oh, okay. So mine is just like a curiosity, in the sense that I understand that the idea of using these initial states that are basically pure states of the dressed 2 qubits. I mean, I understand that this is more simple than starting with some sort of entangled state or something more complex. But my question is just, if depending on the nature of the noise, do you think that it could be useful actually to start from a different kind of initial state, that it can just, instead of just complicating things, can, I don't know, help to, in particular, to get information of the correlated part of the noise?
Maybe I can try to answer this one. I think this is a very good question, and very, I mean, I would say this is up to, more work would be needed to establish that. So experimentally, we wanted to focus on the states that were easily achievable in the lab, but it's possible that the initial entangled state would give us more signal. For example, if you look at these 2-qubit observables that we measure, they always start at 0 value, and then their value increases roughly over time, and then they oscillate somehow. And this means that for in the beginning of this evolution, your signal to noise ratio, so the value of this correlation versus the error bars, it's not very good. So maybe with an initially entangled state, you could start off with a higher signal, and this would help actually. But this is really up to more fundamental research would be needed to answer that question.
Okay, thanks.
Okay, thanks. Maybe then the next question by Hugo Döllemann.
Yes, hi. Thanks for a great talk. My name is Hugo. I'm also joining from the ETH in Zurich, as Uwe knows. And my question was also about one of the last slides that Uwe showed. Maybe you could show that with the 2-qubit noise spectra. So you already mentioned, like in the top 2 slides, that you see more noise than what you predict from photon shot noise. So how would you go about, how can you interpret these spectra to learn about where your noise comes from? If you see, for example, a peak in the spectrum, you know, not a peak that you created, but some other peak, does that mean that, you know, both are coupled to some shared resonator?
Okay, thanks, Hugo. I would say, let's say you have a system of qubits where you have a vibration in your sample. For example, in quantum acoustics, we have these samples where you might have an acoustic resonator in the same sample as your circuit QED resonators, or maybe a spin qubit. Then if you know the frequency of the mechanical vibration that might affect both of your qubits, then you could probe using this protocol this frequency, and then if you see a peak, you can say, well, okay, we have another thing that is oscillating at this many megahertz, and we see it in the cross spectrum of the 2 qubits. So this might disturb our results. This is basically the same thing that you would do for single qubit spectroscopy, where if you have a known source of oscillation, maybe in a flux bias or something, as in this original, in this paper from 2013 I quoted earlier, then you could perform the spin locking relaxometry at this Rabi frequency and see if you see something.
I see.
Maybe I can ask a quick question to that. So do you, I mean, do you have an idea of how sensitive you are in terms of, like, you know, frequency of the noise and sort of strength of the noise? So what would be sort of the limits there?
Yes, that's also a very good question that I couldn't address in the talk. So if you look at this sketch of a Bloch-sphere here, you can imagine the strength of your Rabi drive, so this omega, as a vector, like an oscillation vector that points along the x-axis. And if your Rabi drive is not 100% on resonance, right? I mean, it will be very much on resonance, but there's always some difference. Then this means basically that this vector isn't pointing along the x-axis, but along some angle with the x-axis. And the ratio between these two will determine how accurately you can apply the spin locking drive, such that the experiment that you perform can be matched by the master equation simulation later. So this is one factor that determines the accuracy. Other than that, I would say I like the idea of the entangled states that Santiago brought up earlier, but also the number of averages, how constant your experimental parameters are. So, for example, the T1 of the qubits can vary over time, and the T2 as well. So the native noise can change, for example, by two-level systems fluctuating back and forth, and this will also cause, of course, your experiment to be less accurate. And number of averages in the end, so the measurement time that you can perform this.
Okay, thanks. So Malay Singh had another question regarding fits, so maybe let's do that one next.
Okay. So the question is that from the paper, I see that some of the parameters that go into the fit, they could be independently extracted from the experiment. And, you know, you could have just done a master equation simulation to just match the experiment, like without even fitting. Could you have done that?
Are you thinking of Chi1, Chi2, kappa, etc.?
Yes.
Yes, we do have some measurements and independent measurements of these, but they are not accurate enough. So that's why in the part 3 of the paper we do these fits to the full master equation, including cavity and the 2 qubits, and this turned out to be more accurate in the determination of these parameters.
But why are those measurements not accurate? Is there some fundamental limitation to measuring those accurately?
I do not believe it is fundamental, but I should ask Uwe to complement on this. He's the one who did these measurements.
Yeah, so I would also say with other independent methods, you can measure them as well, and we did, and used this basically as starting points to then use the fit in the paper to find them more accurately. So I think what we used in the end to fit the parameters was this separate Ramsey experiment and the initial this comparison, and yeah, well, I guess you should also be able to measure them independently, of course. Yeah, I guess, yeah. We didn't, but we did measure them independently and then still use this fit. But the values also that we measure independently are, of course, basically the same. If you just measure your chi and stuff.
So I asked because in my experience, let's say if you're trying to target some certain length 2 qubit gates, you need to do these calculations very accurately, and I mean that in principle works. So I was wondering why would these parameters not be accurate, like from an experimental measurement? Okay, right.
Yes, they would be accurate.
Right. If you're coupling 2 qubits, then through, let's say, for example, a bus resonator, and then these, to calculate the effective coupling, you need to find out the qubit to resonator coupling and things like that, and that's how you target the length or the amplitude of a 2 qubit gate pulse. So I thought that would be pretty accurate, those calculations.
I think this could be done. I'm a theorist, so I think Uwe should confirm. I think it should be done. It's just the data we had available at this point. We had more data using these master equations, and we could make more accurate fits. But I would tend to say that if one wanted to precisely measure, devote some fridge time to precisely measure chi1, precisely measure kappa, precisely measure chi2, this should also be possible.
Okay. Okay, thank you. Thank you.
Okay, let's move on to, I guess, maybe the last 2 questions. So maybe next one by Matt Eager.
Oh, I was just wondering, was this at liquid helium temperature you did all this? Or I was wondering if maybe the additional noise was from, from phonons in the system.
Okay, so we performed this at the base temperature of a dilution refrigerator. I think the exact temperature is around 20 millikelvin. The vibrations that arise in the system, for example, from the cooling mechanism, are not even close to the frequency. So I doubt that the correlations come from phonons in the system. Actually, also the thermal occupation of the resonators isn't strong enough. And as I indicated before, we measured the same experiment here with the noise drive off. So that would probably not show a different result if the correlation came from a different source. Thanks.
Okay, then we have a question by Christine Beck.
Yeah, hello. Thanks very much for the talk. Can you discuss the sensitivity of this technique? You sort of did this a little bit in your discussion of the overall sensitivity, but in particular to the control noise and noise on the Rabi frequency. Thanks.
Are you mentioning fluctuations in the Rabi frequency?
Either fluctuations or just the overall noise spectrum being something that's less than ideal.
Yes, so that's an interesting question. Actually, the paper discusses some issues related to drifts in the Rabi frequency. It's very important for this protocol to work well that the two Rabi frequencies be almost the same. And if they are not exactly the same, then the correlation terms in the master equation, they have some oscillating behavior at the difference Rabi frequency. And this means that over longer times, they will be washed out. And so that is something we had to take into account actually in our reconstructions. Yes, Uwe is pointing to you. This is used as a ninth, this frequency difference is used as a ninth fitting parameter. If we had a broader spectrum, this would probably be less of a problem because that frequency difference would be very small compared with the width of the spectrum. But in this experiment, it was important to keep this fitting parameter, additional fitting parameter. So you can see on the inset of this plot that this with this estimation technique, we can actually see this delta omega having slow drifts over the time during which the experiment is done, because we did this 1.8, we did the sweep of omega from the smallest to the largest value. So you can see it, you can see actually drifts over the several hours that were needed for this experiment to be completed. So it is indeed something that needs to be taken into account. But now if you're thinking of really looking at the frequency dependent of these fluctuations, and I don't think this technique would be directly usable, but maybe you can derive a master equation that includes these effects. But this is something we didn't do.
So maybe I can pick up on this question. So in general, of course, one would want to have like a characterization toolbox, which is able to describe both background noise, in this case it was predominantly dephasing noise, as well as noise which is introduced by the control itself, which I think is what you're getting at. This particular technique was not designed to do that, although it could still be improved, like Felix said, to address some of it. However, there are, and we have been working also on different characterization noise spectroscopy techniques using different principles than spin locking, where there is the possibility to disambiguate, let's say, for instance, an additive dephasing source, and like imagine you have a multiplicative control noise on the Rabi frequency, and it's possible to try to spectrally resolve the two of them separately. This is a different work, a different paper, but I have to say that in that case, the noise was taken to be classical, and also it was a single qubit demonstration. So the upshot is that there is still a lot of work to be putting together different pieces and capabilities in designing a more complete characterization, so let's say.
Okay, so seems like we are out of questions. I at least don't see any more raised hands. Maybe I can add another one at the end. So, I mean, sort of all of this is geared of sort of maybe characterizing like quantum processes in the future. So could you imagine how you would scale that to sort of even larger systems? Would then sort of like just pairwise measurements like these be enough, or would there be something more I could learn by maybe involving more qubits simultaneously?
That's an excellent question. There is actually a section at the end of the paper that discusses these issues. I think Lorenza probably has a more complete point of view on this than me. So I don't know, Lorenza, if you want to weigh in.
I can happily weigh in. However, Gerhard, I think you touched upon, certainly from the theory point of view, this is a main open question as to scale up characterization techniques to the, even just to the NISQ size, and possibly beyond. In two ways. On the one hand, there is the question of like how to modify the protocols to handle bigger systems. And I could imagine, for instance, that if you have the capability to do 2-qubit measurement or to handle pairs of qubit, you could use a technique like the one we have demonstrated, but maybe by choosing certain pairs, possibly at random, possibly according to some intelligent scheme. But the flip side is also that as we scale up the system, we probably, or actually certainly I would say, we don't want to have a fully complete characterization. You certainly wouldn't want to have a huge list of all the possible correlation functions with the real imaginary part, because that information would be too much. Even if, let's say, we could have it potentially, the question is like, would we want and would we need to have that much? So where exactly to strike a balance for how much information would be enough for the purpose of characterizing quantitatively and predictively for what? For instance, for tolerant regimes, that I think is a widely open frontier in QCVB.
Yeah, maybe this is Will. Maybe I can add to what Lorenzo is saying is, I agree with that. And one of the challenges we're going to face in scaling up is developing what you might call reduced complexity models.
Exactly.
Are, if you think of a Swiss Army knife as being able to do everything, we of course need the Swiss Army knife when we're figuring out how these systems work. And I would say what we've presented here today is really, a method that really helps us understand what's going on, but its application to a large scale system probably won't occur in this way. I think we can say that. And the abstractions that we need to make to take what we've learned here and apply it to a larger system, those abstractions still need to be made. And they need to be made in a way that give us the information we need and no more, because all of this is very, very expensive to implement. So that's the challenge going forward. But of course, we can't develop abstractions until we know the full picture, right? And I think that we're at the point now of developing the full picture.
Yeah, exactly. Understanding, like Will put it, like all the information, no more than that, but also no less. So what we need to do what, that's part also of the challenge we face. Because for instance, if one wishes to have a multi-qubit sensor for metrology, maybe the type of information that is necessary for characterizing the noise is not going to be the same that it might be needed for a device to operate like a fault-tolerant processor. So as a theorist, I think this is a challenging problem. Also because most of when we think about fault tolerance, most of the error models that have been used in theoretical analysis of fault tolerant operations, they don't work with this type of like spatiotemporally correlated processes that we have been targeting here, which to some extent are found in realistic devices.
Yeah, thanks. Thanks to everyone for participating. Thanks to the authors for answering all the questions. And maybe let's thank the speakers again, and then I'll hand over again to Katyusha.
Yeah, so thanks so much, Felix, and for the nice talk, and for all the authors for being here. And also special thanks to Gerhard for this moderation and everyone for the participation at all. I just put in the chat, I just want to highlight that we have a web page for the Journal Club. So please check there for the next events, about one per month. So thank you so much. Have a good end of the day, everyone. Bye.
Thank you, Katyusha. Thank you, everybody.
Thanks.
Thanks. See ya.
Bye.
Bye. Thanks.